Hi, today I'll present how what we have learned so far at AI is relevant to natural language processing. So first, we talk about why it is important to understand human language. First, people reflect what they already know when they say something or write something. So understanding human language in spoken or written form is a rich source to collect human knowledge. And also when machine can understand human language, we can implement very natural means of interfacing, like talking to computer to get something done or ask for information through natural language. Corpus is a collection of text from which we can train lots of AI for language understanding. For this course, I want to introduce two sources. First is NLTK, which is a Python library for everything related to language processing. So this is something you want to play with. So here is a snapshot from NLTK, which also has a very easy access to a big corpus of existing novels, such as Jane Austen's Emma or Persuasion, Sense and Sensibility, and so on. We can get the full books for free because their IP has expired. So this Gutenberg.org is the URL, which is collecting all those free text that can be used for research purpose. So for those books available, free books available from Gutenberg, we can use NLTK to write 4 lines of Python code to understand the probabilistic characteristics of those books. So for example, the num character is, so here there is a list of books where the first column is the number of characters divided by words, which means average number of characters in each word, which happen to be 4 for most of the books. And then we can also average number of words divided by number of sentences, which will give you the average number of words per each sentence, which is usually in the range of 17, except Milton's book, which has 52 words per sentence on average, which means this book is quite verbose. And then, so we can do lots of statistics with just 3 or 4 lines of Python code thanks to free corpus and free libraries NLTK. NLTK also has a collection of web and the chat text. So today we'll talk about lots of probabilistic techniques which we have already discussed in class. We can use this knowledge to build interesting AI tools such as automatic classifier that can tell who is the author of the book we are reading, whether it is coming from the web or book, and so on. So for example, there is a snapshot of web text that is available from NLTK. Okay, so we can use this corpus and their statistical analysis to identify who is the author of the book, whether the text is coming from the chat. And a very good example of AI that we use every day is classifier that identifies whether the email is spam or not. What's interesting in the field of NLP is that there are many open tasks so that researchers around the world can compete on the same very well-defined task. So one example is a task described here based on Reuters corpus, which is basically a corpus of news articles. So there are 10,788 documents with 1.3 million words, and it is already classified into topics such as sports and so on. And then they divide it into 2 sets, which is for training and the test. So what you can do is that using the training part of open corpus, you can train your classifier, and then you test your classifier on another set called test. Since all the researchers are using the same training and the test set, you can just release your accuracy in terms of this set as a part of your paper, and then anybody else can you know how good your result is, so they don't have to implement your method to argue their work is better than ours. They can just simply show the number that is better than ours, assuming nobody is cheating. So what you can do with this task is using training set, which is basically a news article that is already classified into topics, so that different topic group has human given labels already. And then the testing set also has label, but you just use it for evaluation purpose. So you already trained your classifier, and then you will do the prediction based on your classifier trained on training set to predict the label of each testing document, and then you compare with the label based on which you will be able to compute accuracy. So how exactly we can do accuracy, we can calculate accuracy, will be revisited later. So from there, because from the labels, you already know which set of the documents are relevant. And then there will be another set that is returned from your system. So you can come up with two notions of accuracy. So you can check, so this is good result, and then you can get the ratio of true positive out of all relevant documents. So this measure will be recall. And then another measure will be true positive in terms of out of all the documents that you retrieved, which is precision. So this is a very well-known event. Okay. Precision is proportion of true positive out of all the documents retrieved. Meanwhile, recall is fraction of true positive out of relevant documents shown by human labels. So the question here is, why do we need both matrices? One good example to illustrate why having one of them is not sufficient is that we can very easily build a system that achieves 100% recall, which is returning all the documents they have. So that way we are sure that our result will cover every relevant documents, but we are also sure that precision will be very bad, because that includes all the bad results with them. So people will spend long time pruning out bad results. So usually there is a trade-off between precision and recall. So sometimes some scenarios prefers high precision systems. For example, lots of software companies like Google, Microsoft, their hiring manager is saying that recall is less important. It is not important for, say, Google to employ all the good software engineers out there. Rather, they argue that the precision is more important because they don't want to hire bad software engineers by mistake, for which company has to waste lots of money and time to train this person. So in this specific scenario, we'll try to build high precision system. Or when the scenario doesn't prefer high precision or high recall system, people try to find a good place where both precision and recall is high. So here the graph shows a trade-off between precision and recall. So sometimes you can shoot for a break-even point where precision and recall value is the same, or you try to optimize for F1 measure, which is combination of precision and recall, to find a system that has strengths in both precision and recall. We have discussed lots of probabilistic models and a little bit of machine learning. So I'll show you how our knowledge about these two techniques can train ourselves to join the task like document classification. The goal of probabilistic modeling is that given a task, for example, whether you want to tell whether the given text is a spam or not, you want to build a function that can map the given text into the probability that this text is a spam. So for example, here we are given with this text, hello, do you want free printer cartridge? Maybe this is likely to be spam, free is suspicious, and large capital is usually a indicator of spam. So we want to train a model that can give a high probability for this text to be a spam. For that, we need to learn the concept of language model. So that is a fundamental concept in NLP. So if we build a language model for, say, English, this model will tell you that certain word, like the, is very likely to happen than others, something less frequent such as beautiful. Or this model can reflect that two words are likely to follow each other. So for example, walls, street usually comes with each other. So this model will help a lot of intelligent tasks on language. I'll show you example. So as a human being, we are quite familiar with common sense knowledge that if I see a sentence like stocks from the wall and some missing word, it is very easy to guess that the next word is street because we are trained with lots of English text that we have read or studied so far. So we can very easily guess the street will be the next word. And then let's think about some speech recognizer, machine speech recognizer. Let's say Korean speaker was saying something in English. A lot of time we fail to make the difference between fell and tell. Then even though we make a mistake, given what we have said so far, stocks from the Wall Street can fall or rise. So among these two, we can very easily tell based on our common sense about English, which is language model, that fell will be the right word. So even when a speaker make mistake or a speech recognizer make mistake and do not know which one is better or make error to guess what's been just said or what's been just heard is pale, it is very easy to fix the error based on our understanding of English. So that's why we need a language model. So it can be used for translation when you are translating something from Korean to English. You want to say that winds will be very strong. Maybe you, based on your understanding of English, you know that strong or high will be a better choice than large, even though three words have similar meanings. And from spell correction, people may say 15 minuets. But from your understanding of English, you know that probably this person means 15 minutes, even though minuet is a right word. It will probably come with musicians or music, so based on your understanding, you know that minutes are right. And from speech recognition, even though this is what you have heard, you know that this is more likely to be the English word, so you can replace each wrong word with the right word, likely word with similar sound. So that way your speech recognition will be very accurate. This can be used for pretty much any language task. So the most simplistic language model we can build is just unigram. So this language model can be learned by 3 lines of Python code, again with NLTK. You can just get the frequency of every word. So that will be for each word, you get the frequency of each word. And then this is unigram or 1-gram model, and you assume independence. So if you want to know how likely in English to see I like AI, then you can just simply how many times I appear and then like appears and then AI appears in the English text. And if this score is really high, then that means it's likely that this is correct sentence for. However, unigram is not perfect. So to illustrate, there is an example sentence here. So Mozart something is pleasant to hear. Based on unigram model, if you are trying to compute whether having minute is higher probability for making this sentence to be a valid English sentence or minuet, then unigram will tell you that minute, because the probability of minute is much higher in English text than minuet. But considering Mozart, or it is talking about here, or music, minuet, the probability of minuet in general is very low, but given we are talking about Mozart, maybe this probability is much higher, even higher than having minute. So this kind of idea of conditional probability or joint probability is not very well supported by unigram. So to recall what we have discussed about joint probability, the probability of Mozart, minuet, and these four words together is based on the chain rule. It looks like this. So revisiting Markov assumption, they make some kind of assumption that maybe the probability of seeing minuet after everything is the same as seeing the last word or the last two words. So Markov assumption will make simplifying assumption that maybe the probability of seeing minuet is depending on the word before that, or two words before that, or a few words before that. So that's the idea of n-gram. So you will see, and this is example Python code of collecting two gram. So how likely to see blue after Berkeley, or gold after Berkeley, and red after Stanford. So just like Yonsei University is recognized with blue, Berkeley is recognized with blue, so this conditional probability will be very high. And going back to our example, minuet is likely to follow Mozart or any other composer. So this correlation will be collected in this bigram or 2-gram idea. So basically this is the Python code, which is collecting two words next to each other and their frequency count. So this statistic will find wall street together, the frequency of street given wall. So this will 2-gram will collect the conditional probability between two words, and then of course this will require much larger storage space, because unigram you only need to keep the statistics of, if there are n words, you just need frequency for n words, but for 2-gram there are virtually n square possible pairs for which you need to store frequency. So storage wise, having bigram as a language model is more costly, but in terms of predicting next word or finding more reasonable translation, 2-gram will have a better result. And of course you can think about the bigram or 2-gram is better than unigram or 1-gram, And you can, of course, if your storage allows, you can do the trigram, 4 grams, or 5 grams. But this is, well, even though you make it 5 grams, this is not perfect because sometimes dependency, the Markov assumption can be quite limited when there is a dependency, but it is far, far away from each other. So here, computer, of course, is correlated with crash, but because it is described by very long clause, this dependency cannot be captured by 2 gram or 3 gram or 4 gram or 5 grams. So this dependency will not be captured. So since this clause can be arbitrarily long, no matter how big you can store, this kind of long distance dependency can be lost. So that will be fundamental limitation of n-gram. But recently there was a news talking about AI that is written in Japan that automatically wrote a novel, the science fiction novel. It was submitted to for some prize, and the judges could not tell whether the novel is written from a machine or a man. So it almost made almost won the prize. So that was quite shocking news. So you may wonder how exactly this kind of AI can be written. That must be really hard. Of course, writing this up to the level of winning a prize will be very hard, but doing it at a simple level is actually doable by undergrad as well. So this is 3 lines of code which can do a similar thing. So your sentence will start with creature, and then for root, we are going to write a sentence with 20 words. So basically at the loop, this is bigram model. So among the word that co-occurs with creature, what is the most likely next word? And it turns out to be that. So, and then in the next loop, in the next iteration, what is the most likely word that follows that, which was he, and the most likely word that follows he is said. So that way, this is the outcome of the sentence automatically written, given just one word. The creature that he said, I will not be a wife of the land, which is weird, but still, it somehow looks like English. But this is done by bigram, and there are at researcher level using higher level statistical resources like n-grams. It is getting better and better in automatic writing. So this is example of writing something that Shakespeare would have written using unigram, trained by lots of Shakespeare model. You can see that Shakespeare used lots of old word and like this, which is not frequently used in modern language, but it has high probability in Shakespeare's work, so it will appear in unigram. But it doesn't read very well. To him swallowed, confess here. Both it's too many verb. Then you can replace your model with bigram, and then it reads much better. What means they are likely to co-occur. The King Henry is very likely to appear in Shakespeare, and if you use trigram, that sounds much better. And quadrigram, that almost the sentence almost makes sense. King Henry, what? I will go seek the traitor, which is what I would say. So this is, I think, illustrating the importance of language model. And if you have a good model, then you can build lots of interesting AI. Those creating language, classifying language, classifying documents into spam, and so on. And the quality of intelligence also depends on how big your data is and how good your data is for training a model. And Google has a big advantage because it can basically read. It is reading the entire documents on the web every day, so they are releasing 4-grams and 5-gram trained with virtually all the books, all the English books on earth. So this will be a very good, high quality, big and high quality resources to do the language intelligence work, and that they are released. So if you are curious, you can visit this URL to see these 4-gram models and 5-gram models of English. You can imagine having this kind of 4-grams will be very helpful when you are hearing something from somebody and then you weren't sure whether he said popcorn or unicorn. Then since it is talking about theater and people buy lots of popcorns there, and that kind of correlation will be represented by 5-gram or 4-gram. So based on that, we know that popcorn will be the right result when you are not sure whether you heard popcorn or unicorn. And also after translation, you can check whether how good this sentence is likely to be a valid English sentence using your model. You can do it by, when you are using unigram, that will be the probability of each word, multiplication of all those probability. But when you are using bigram, that will be, you will compute it based on the Markov assumption. N-gram model will be built from the training set. So this will work very well if the testing set, like a translator, their probability is actually the same as what you have observed in the training set. A lot of time it is, but there are also times that it doesn't. So the biggest problem is word that has not been seen in the training set. So for example, if there is a new word coming out, so when you are trying to understand the Twitter, if there is a new word, XU, let's say this is the new word, this has not been observed in the training set, and of course the probability will be 0. So any sentence that has this new word will have very low probability. So this is an example of overfitting because the reason the probability X is 0 may sometimes mean X cannot be a valid English word, but sometimes it may just mean that we didn't have a chance to observe this in the training set. Training set is simply a sample of possible words, and then this sample is limited such that we didn't have a chance to see the word. So having this as a 0 probability will degrade the quality of the intelligence system that is built on language model. So basically, things that didn't occur in the training set may or may not mean that this shouldn't happen in the test set. So dealing with zeros in an intelligent way will make a big difference. Let's say we have observed, denied the allegation, the report, and the claims in the training set, but this is first time seeing it in the test set. This probability will be 0, and then we'll reject this as a valid sentence, but it is actually valid sentence. It is just that training set is limited, so you couldn't see the offer. So to better generalize, we do smoothing. So even though from our training set, even though we haven't seen attack or man or outcome, well, this may mean that this is not the right word, but it may also mean that this is possible word, but because of the training sampling, we haven't seen it. So in other words, the actual probabilistic distribution of word will be very smooth if we could observe every word. But since we have limited observation or sampling, it looks very discrete. So maybe we want to make this discrete observation into more smooth thing by borrowing some counts from those words observed to make this probability non-zero. So this is called L1 or Laplace smoothing. So I'll show you how we do it. We just pretend we saw everything one more time. Okay, so we may have not observed something, but we'll give you 1 as a default count, and that makes every word to have 1 extra count. So when you are normalizing it, you will have to divide it by the number of words. So let's say B is the number of words. So this is an example of smoothing. So before, we haven't seen anything, any bigram that want is followed by want. This is maybe because we never say it like that, so the probability is 0, but since there is also possibility that it is possible but we just couldn't have a chance to observe it, we'll give it a very small score. And then you normalize it, and then the table will look like this. So we can interpret this as this. So usually the sun is setting in the evening, but one day sun may go up again in the evening as well, which will scare anybody. So based on my life observation, I'll say sun will be setting at 6 p.m. and sun never rises again at 6 p.m. I'll give it probability to 0 because I have never seen it in my entire life. But wise thing to do is giving it a little bit of probability, because it might be possible that I only lived certain years, and if I live 30 more years, this may happen, right? So we smooth it by giving some a very small score. So for example, if you achieved R twice and B once, you just assume you have observed one R and B one more time. So if you just do not do smooth, your probability is that out of 3 balls, 2 of them are red, 1 of them are blue. But if you are adding 1 more R and B, you are now out of 5. There are 3 red and then 2 blue. And even though you haven't observed something, it may have some probability. And you can generalize it to add k instead of 1. So when k is 0, it is just you do not add anything. So there are 2 balls of red, 1 balls of blue divided by 3 balls total. When k equals 1, you will add 1 more R and 1 more B. So it will be, red will be 3 out of 5 and B will be 2 out of 5. And when it is 100, you are adding 100 of red balls and 100 blue balls. So it will be 102 red balls and 101 blue balls divided by 203. And in better writing, now that we have learned about language modeling, how we can use unigram, bigram, or trigrams or upwards, and then we make sure our language model generates better by smoothing for the words that have not observed in the training set, will give small score. So we talked about L1 smoothing or Laplace, and then we can actually generalize it to consider at k. So when k is 0, it is just without sampling, without smoothing. When k is 1, it is Laplace. And when you can try to vary those k values to make the model that works best for you. So our next question is, what is the application scenario that we can use this language model? One example is spam filter. So the goal is when you are reading email, when you're getting email, you want to know whether the email is a spam or not, to put the spam into the spam folder so that you wouldn't waste your time reading spam. So for training your language model, you will have a collection of emails that are labeled, hand labeled as spam and non-spam. So for example, you will have 10 emails where some human beings labeled as spam or not, and then you will train a language model so that you can build an automatic classifier that can see a new email, and then without human judge, they will know whether it is spam or not. So we'll talk about, we already know how to build a language model from a collection of email. Then once we have it, how do we use to build the automatic spam filtering? We'll use a naive Bayes method. The goal of naive Bayes will be predicting whether Y label is spam or ham. To calculate the join probability of spam given the words in the email, you can compare the probability of spam and then the probability of words that the language model of spam emails, and then you can compare it with ham, the probability of ham, and the language model of ham emails examples that are human labeled. So this is concrete example. So for label, we make humans to label say 100 emails into spam and ham. So what you need to record is how many of them are ham, or which is normal email. So 66 of those are okay email, and the rest of it is spam. And then you will take a look at only the emails that are classified into spam by a human, and then you create, say, unigram model. And then you can take a look at the ham, the right emails, okay emails, and then you will see the distribution. Then, so you will use the training data to build a language model for spam and the ham. So from this training, you will learn the probabilities, and then for smoothing, you may want to tune K, and then you will use different data where without label, but there will be label, but only for the evaluation purpose. So if you use this, if you take a look at these labels for training purpose, you are cheating. You shouldn't pick the labels in the test set. So you will just take a look at the labels of training set, and then you'll train your classifier using that. And then you will test your data using test set and compare predicted results with labels, and then you will report accuracy based on this test data so that your result can be compared with other people's work.